This is our PDR presentation. We are Operation Asteria from George Mason University. We are working in cooperation with the Thomas Jefferson High School for Science and Technology, the Chantilly High School, and the George Mason SATCOM Club. Today we'll cover our team introduction, mission objectives, changes made since the proposal, payload, expected outcomes for each mission objective, Gantt chart, questions for PDR, and our appendix. Our team includes a mechanical engineering team, which is run by Mr. Gallo, our electrical and computer engineering team led by Dr. Pakowitz, and our systems engineering team led by Dr. Sherry. Our mission objectives cover our 3 experiments that we plan to do. The first one being battery thermal shielding, where we will have an installation and ensure that it can withstand the extreme temperatures of space. Experiment 2 will be our UHF spectrum analysis experiment, where we will take frequency and RSSI data in the amateur radio band, and with that determine good communication frequency for future missions. Experiment 3 is our power system comparison, where we'll compare 2 power system architectures on a ThinSat. Our mission requirements cover our 3 experiments with the battery thermal shielding, the UHF spectrum analysis, in the amateur radio band, the comparison of DET and MPPT power systems. Also, our communication between our payload and the ThinSat onboard computer. We also have a limitation of 100 milliamps of current draw, and the ThinSat payload shall operate in a vacuum of 10 to -8 torr and temperature range of -30 to 60 degrees Celsius. Also, some requirements we have to discuss with the PDR board later include our payload limit of 72 grams, the payload dimensional limits from the interface control document, and also modifying the ThinSat plus Z side to accommodate our solar cells. So each experiment has success criteria to ensure a successful operation. Battery thermal shielding will verify that in the temperature range of -30 degrees to 60 degrees Celsius, the battery stays within 0 to 30 degrees Celsius for a safe operation. Also, the battery box must survive the launch environment, and from this we'll be able to determine the optimal insulation between the 2 that we compare. Experiment 2 is our UHF spectrum analysis, where we will take frequency and receive signal strength intensity data between 433 to 440 megahertz. From this, we will develop a repository for future missions so we can determine the optimal frequency to use for satellites communicating with the DC metro region. And experiment 3 is our power system comparison, where we will compare the DET and MPPT power structures, collecting current and voltage data to develop current voltage curves, and from this we'll be able to determine which of these is the more effective approach on a ThinSat. Since our initial proposal, we added the UHF spectrum analysis experiment, and of course this still is keeping us limited to our space and weight limitations provided from the Virginia Space Program.
So as you can see, this is the overview of the payload. So in this box here you can see experiment 1. We're hoping to connect experiment 1 to the beacon interface so that we can send our temperature sensor data down to the beacon interface using the telemetry. Experiment 1 is going to be scheduled by the microcontroller. So is experiment 2, and so is experiment 3. Experiment 2 is going to contain a UHF receiver and an antenna. This antenna will be a monopole antenna attached to the outside of the ThinSat. Experiment 3 is going to contain sensors, variable loads, the DET and MPPT systems, and then solar cells for each system. All 3 of these experiments are going to be scheduled by the microcontroller, which will have power protection with latch-up, watchdog timer, and soft restart switch. And they're all going to be receiving power from the 3-volt power ThinSat bus and the beacon interface power, with the exception of experiment 3, which will be run off of the solar cells that we have to mount. So this is just a more advanced schematic of the payload. So over here you have experiment 1 with the different temperature sensors. We can have up to 6. Over here you have experiment 3, or experiment 2, which is the UHF chip and the monopole antenna. Then you have the payload connection, the MSP430, and the experiment 3 comparison. Onto the structural layout. This is the structural layout of the ThinSat. So over here you can see the ThinSat battery box, which will be in the middle, closest to the center of gravity, center of mass of the ThinSat. We're going to have the DET MPPT experiment on the top, which will be, as you can see, directly above the solar cells over here. The solar cells will need to be in a cutout on the back. So the cutout we're expecting is a 46mm by 32mm cutout. This is subject to discussion later on. We are going to then put the MSP430 and the UHF chip on the bottom. This will be closest to this interface port between the payload bus and the payload. So we need to mount multiple things onto this ThinSat. We need to mount solar cells for experiment 3, and we need to mount a monopole antenna. And so we're going to discuss this later on in a questions section, because this is just open to discussion at this point. So moving on, experiment 1, we have a thermal battery shielding. So the plan is to keep the battery box above operating temperatures, or within operating temperatures. We're going to use 2 different types of insulation to see which one is better. And we're going to have a couple requirements for this experiment. So basically we need to keep our experiment limited to 36 grams. We need to keep the temperature between 0 and 30 degrees Celsius. This is the battery operating temperature. We need to keep, we have to worry about vibration, so we have to withstand 2,000 hertz of vibration for 8 minutes. We need to worry about vacuum, so we need to be able to withstand decompression of the launch. And then we need to worry about launch forces, the acceleration and the thrust. So when choosing the battery box design, we chose different materials for the battery box. So this is why we chose each material. So for the frame, we chose aluminum 6061 T6. We chose this because it has low density, high thermal conductivity, good strength to weight ratio. We chose our temperature sensors, which are the LMT86. We chose these because they have a small footprint, low price, and they don't need additional circuitry. For the installation, we chose MLI and Kapton tape. We chose these because they're lightweight, high emissivity, and they are very thin. We chose a Apollo lithium polymer battery. This battery was chosen mainly for its weight and size considerations, but it also has a 500 cycle lifespan, so it's perfect for small missions. So we're planning on constructing the battery. As you can see on the right, we're going to have the battery frame, then we're going to put the Kapton insulation tape, or whatever insulation we use, on the inside, and then we're going to put our polymer batteries inside the battery box. So this is the interfacing for the experiment 1. So as you can see, it's similar to the options we saw before, but it's just a little bit more in depth. So this is our battery box, and we have these 4 different temperature sensors. These 4 temperature sensors are on different parts of the battery. So one's on the outside of the case, this is on the other side of the case, and then one's on each battery. These temperature sensors are going to go directly to the beacon interface, and they're going to be scheduled through the microcontroller. It's going to be receiving the 5-volt power supply from the beacon interface, so that's how we're going to run that. So there's 2 options for this experiment. We're thinking of testing currently 2 different batteries and 2 different thermal shields, but if we have weight problems, we can move down to 1. So some preliminary simulations we've done for this program is we did a Fusion 360 axial loading simulation. So what we did is we put 20 Gs of force onto the battery box in the direction of the rocket thrust. We had an acceleration of 184.3 meters per second squared, and we used the thrust of the rocket to determine these. Then we fixed the battery box by its holes and bottom face, and the result was we have very minimal stresses. Any deformation is elastic deformation, so it is not permanent, and the max stress is at the screw joints and the middle part. So the next simulation we did was an internal fatigue random vibration test. So for this test we went 20 to 2000 Hertz based on the NASA STD 7001B test standards, which are down here on the right. We ran this simulation for 8 minutes, and we again fixed our battery box by the screws in the bottom face, with the similar result of no permanent deformation and the max deformation on this crossbeam and at the screw holes. So we secured the battery using a spacer so that they would not move.
In this experiment, we will measure the received signal strength indication, or RSSI, on the ultra-high frequency subband between 433 MHz and 440 MHz. With this data, we will construct a frequency spectrum analysis graph to determine which frequencies in the subband have the least terrestrial noise. Here, we have a list of requirements for the experiment in regard to mass, temperature, vibration, and vacuum. This diagram shows the interfacing between Experiment 2, the payload microcontroller, and the ThinSat bus. We will use the RFM69HCW UHF receiver chip to collect RSSI data, although we are considering a few other radio modules. The UHF chip will connect to a monopole antenna and to the microcontroller. The microcontroller will control the experiment. When it is time to activate the experiment, the microcontroller will enable the switch, and power will pass through a filter and go to the UHF chip. The microcontroller will communicate to the UHF chip through SPI, and the chip will send RSSI data back to the microcontroller. Experiment 3 is the power systems comparison. We will compare MPPT, maximum power point tracking, and DET, direct energy transfer, to determine which system most efficiently delivers power to the satellite. Here we have a few requirements in regards to mass, temperature, pressure, and vibration. This diagram shows one half of the setup for Experiment 3. We will collect light data and temperature data to determine when the experiment needs to be activated. Here we have the DET solar cells connected in series, going directly to the load, which is shown on the next slide. Here we have the MPPT solar cells, which are connected in parallel and go to the MPPT chip. We plan to use either the SPV 1050 chip or the LTC 3105 chip. From here, the power will be sent to the load. This diagram shows the variable load setup for Experiment 3, which is based on research done at our university. Both the DET and MPPT power will be connected to the variable load, as you can see here. The variable load will be controlled by the microcontroller and connected to a digital to analog converter and a filter. The current and voltage from the DET power and the MPPT power will be sent to a multiplexer, which will send data back to the microcontroller. This diagram shows the microcontroller protection for the payload to prevent single event upset of the system. Power from the ThinSat bus will be sent to a soft start switch. The soft start switch will be connected to a current sensor, which will power cycle if needed. The soft start switch is also connected to a watchdog timer, which can turn off all hardware if needed. Here we have the scheduling for the experiments on the payload. Experiment 1 will run during sun and eclipse and will send temperature data through beacon frames. Experiment 2 will only run during sunlight because it uses power from the ThinSat bus. There are two options for this experiment. We would like to activate the experiment only over the DC area. However, as we learned during our PDR presentation with Virginia Space, the GPS on the ThinSat will not be accessible during orbit. So we will have to run the experiment at all times and collect any data available. Experiment 3 will only run during sunlight because the DET and MPPT solar cells need sun exposure. This is a preliminary description of the data frames that we plan to send from the payload to the ThinSat with our experimental data. We will have 1 byte for experiment status, 1 byte for microcontroller status, and 33 bytes for data. Experiment 1 will send data through beacon frames. For experiment 2, we would like to send 8 frames of data, 1 for each frequency in the subband. For experiment 3, we plan to send 3 frames, 1 frame with DET current and voltage, 1 frame with MPPT current and voltage, and 1 frame with light and temperature data. The expected outcomes for each mission objective are as follows. For Experiment 1, we would like to better understand the thermal shielding needed to maintain an operating temperature for a lithium polymer battery. This will be used to design a better battery box for small satellites. For Experiment 2, we would like to use our RSSI data to define terrestrial noise in the DC area and determine which bands can be used for a CubeSat communication link. For Experiment 3, we would like to define the efficiency of DET versus MPBT in a space environment.
Here we have our milestones developed by Virginia Space, which includes scheduling the PDR, launching the FlatSat, and completing the PDR. Also scheduling the CDR and completing the CDR in Phase 2 and delivering the engineering model, then Phase 2. Also delivering the flight model for Phase 3. Here we have our Phase 1 Gantt chart, which includes designing the payload, developing test plan, developing the FlatSat, and preparing and completing the PDR at Virginia Space. We'll finish Phase 1 upon the launch of the low-altitude balloon. Moving into Phase 2, we will be designing the payload and preparing the CDR for Virginia Space and delivering the engineering model for the high-altitude balloon launch. Moving into Phase 3, we'll be taking final feedback on the engineering model to develop the flight model and then deliver that to lead to mission operation and data collection. Here we have our questions for the PDR panel that we would like to discuss. That completes our presentation today. Thank you for your time.